All right. Well, thank you very much for the introduction, and thank you so much to Sam and Dallas and Laszlo for putting this all together, and happy birthday to Alexis. All right. So I want to start off by kind of painting a picture of the kind of fluid domain or the fluid regime that I'm interested in, because it's, I think, a little bit opposite to what I think a lot of people who do fluids here think about. So here we are on the microscopic scale, so very, very, very low Reynolds number. And what I'm particularly interested in is in the interaction of these very thin structures, right? So these sperm tails, for example, an example of a very thin structure, with the surrounding very viscous fluid. So that's kind of the motivation for all of the things I'll be talking about. And so sort of where I'm coming at this from is what I'm really interested in is in developing the PDE theory of filament hydrodynamics. And so there's a lot of models that exist in the computational literature for, simulating, for example, a swimming sperm computationally. And what I'm kind of interested in doing is taking some of these models and, from a PDE perspective, more precisely determining the regimes of validity of some of these popular models, and then hopefully, creating frameworks in which we can then talk about deriving, novel models that apply in broader regimes. And so the approach here is to take some of these basic mathematical models that are used primarily for numerical simulations, and justify them from a mathematical standpoint. And so today I'll talk about two aspects of this, starting from a static perspective, and then going into dynamics of an immersed filament. All right, so starting with the static setting, so this I summarize as the mathematical foundations of what's known as slender body theory. And so the picture that I want you to have in mind is, okay, we're just going to take a snapshot in time, and we'll start by considering a closed filament here, with constant radius epsilon, and it's immersed in a three-dimensional fluid domain. So outside of the filament, we have our very viscous fluid that's going to be that's going to be very well approximated by the Stokes equations, since we're at such a very small scale. So we have the Stokes equations outside of our very thin filament. And then if we wanted to most accurately model the interaction of this filament with the surrounding fluid, well, then we would prescribe some boundary conditions, probably some kind of elasticity law over the surface of the filament, right? But as you could see from sort of the first slide, what we're really interested in is kind of filaments that take pretty crazy shapes and evolve over time. And so from a computational perspective, this quickly becomes way too computationally intensive to actually be prescribing boundary conditions over an entire surface. And so this is where slender body theory comes in. So this is kind of a very kind of classical idea that dates back to really the 1950s, with kind of later developments in the 70s. And the idea is just, all right, well, we have a very thin structure. Let's exploit the thinness of this filament. We're just going to treat it as a one-dimensional curve of point forces immersed in our three-dimensional fluid. Okay. And so the way that we can do that is just take the free space Green's function for the Stokes equations, given here by the Stokelet. All right, just take that and integrate it along the center line of this filament, right? So integrated against some force density that's prescribed for this filament, right? Okay, and so this is sort of a good sort of maybe first approximation of how you might approximate the effect of this filament on the surrounding fluid, right? But we can do better, right? We can approximate this better, because at this level, there's nothing yet telling the fluid that there's actually a three-dimensional structure immersed in it, right? So there's nothing here that says, okay, actually my filament has some thickness to it, right? And so this is where some later developments came in to kind of say, okay, how can we tell this fluid that there's actually a three-dimensional structure there? Well, one thing that we can try to impose is that, well, we want to give this filament some kind of sense of structural integrity. And so one way of doing this that people came up with was to just say, okay, one thing that we can do is we can try to say that if you look at a cross section of the filament, the velocity over the cross section of the filament, so if you look at the surface of the filament, over each cross section, the velocity of the filament should be close to constant. And why might that be a good thing to try to impose? Well, you can imagine that, for example, if we didn't have a constant velocity over the surface of the filament cross section, that, for example, say we had a velocity of the field that looked like this, then, well, if you evolve this in time, right, in the next time instant, right, your cross section would deform. In this case, it would get bigger, right? And so that's not something that we want to allow to happen, right? We want this kind of to maintain its kind of cross-sectional shape over time. And so to do this, what's commonly done in kind of the main slender body approximation is to add a correction term to cancel out this leading order angular dependence over each cross section of the filament. So to leading order, if you look at the actual surface of the filament, right, then the velocity field at that filament surface is constant, or approximately constant.
Excuse me.
Yeah.
Just to be sure, there is a minus in S of x.
Sorry?
There is a minus in S of x. The formula here?
Here.
Don't. S there.
No, so there's no minus here. Yeah, so this is, yeah. So, I mean, yeah, this has, F is something that's prescribed, and so there might be a minus sign in there, for example. But yeah, there's no minus sign here. Okay, so this is kind of the classical slender body approximation for the effect of a thin filament of radius epsilon on the surrounding fluid, right? And so this is valid at points that are away from the actual center line of the filament, right? So this is kind of an approximation for the surrounding fluid velocity. And so if you want an approximation for the velocity of the filament itself, well, you can't directly evaluate on the filament center line because this is singular there, but you can perform an asymptotic expansion about epsilon equals 0, and then obtain an expression that gives you an approximation to the velocity of the filament itself, given a force density along that filament, right? And so it's a really nasty looking expression that comes in the form of this kind of local matrix operator, plus this non-local finite part integral operator, right? And so it doesn't look very nice, but at the end of the day, it gives you this sort of reduced dimensional model that approximates the motion of the filament given a force density along it, right? And so this is very popular in computational models because we've taken what was a boundary value problem in 3 dimensions and just reduced it to something that just an equation along the filament center line, right? And so this is a very popular thing to do, or a very popular method that gets used then for numerical simulations, right? So now, where I fit into the picture here is in looking at this approximation. It's not actually clear what we are approximating, and I'll say a little bit more about why. So, okay, so what I really want to answer, first of all, is how close is this slender body approximation to some notion of a true solution, right? And so what do I mean by a true solution, right? And so it's a little bit murky to define this at first, because at the outside, it doesn't look like we should have a well-posed boundary value problem here, because the data that we're given is just this force density F that's prescribed along a one-dimensional curve, right? And somehow, given just this data along a curve, we want to be able to solve for the fluid velocity in 3 dimensions around the filament, as well as the velocity of the filament itself, right? And so at the outset, it's not immediately clear how we can formulate this problem as a well-posed PDE, because it seems like there's a sort of a dimensionality mismatch here. So in order to talk about how good of an approximation slender body theory actually is, we have to know, what are we actually trying to approximate with slender body theory, right? And so to answer this question, we'll go back to the filament setup here. So now I want you to think, okay, this is, a three-dimensional filament here. So it has some thickness, epsilon, right? And it's a solid boundary here. And so outside of this filament, okay, we still have just our homogeneous Stokes equations. But then on the filament itself, I'm going to prescribe some sort of funny-looking boundary conditions. And so this first condition is that I'm going to look at a cross-section of the filament and just take the total force over the cross-section of the filament. So here sigma is the stress tensor, the fluid stress tensor. So I'm going to take the total force over each cross-section of the filament, weighted by the filament surface area. And that's going to be my force density F, right? So that's going to be total force per cross-section. All right, so that kind of makes sense, right? But sort of as alluded to on the previous slide, right, that's not going to be enough information on its own to uniquely solve for a fluid velocity outside of the filament. And so we have to actually make use of this fiber integrity condition, this geometric constraint on the filament where, right, so we want to actually strictly impose that the velocity over each cross-section of the filament is constant, right? So we're going to strictly impose that, right? So we impose that the filament velocity does not depend on the angle of the cross-section, but only on the arc length parameter, right? So in particular, we don't have any pointwise boundary information. We just have this sort of total force condition, and then this fiber integrity condition that the velocity of the filament is only a function of arc length. Yes, question.
Is it possible to perhaps interpret this independence in theta by just averaging around the filament as well?
So yeah, there's maybe other ways to come about, or to kind of come up with a way of thinking about slender body theory from PDE perspective. I'll say why this looks like a good idea. So why does this look like a good idea? So we have this partial Neumann information, this partial Dirichlet information. Why does this lead to something that's nice? So first of all, or really the main reason, is that it satisfies a very natural energy identity. So if you just take this PDE, multiply by U, integrate by parts, then we get this very natural energy identity out of it. So on the left-hand side, we have the viscous dissipation throughout the fluid domain, right? So this is the symmetric gradient. So on the left-hand side, you have your viscous dissipation. And on the right-hand side, where you would have your boundary terms, right? Because of how we've defined these boundary conditions, this actually just reduces to an integral over the filament center line, and we get our force data F appearing in this energy identity, right? And so that's really nice because, first of all, it gives us immediately a solution theory, right? We can just use Lax-Milgram to say, okay, we have, a unique solution for this PDE. And it also gives us a framework in which we can actually talk about doing some kind of error estimate, right? Because out of this, we just get a very nice energy estimate. So in particular, the solution to this PDE is bounded just by that force data that we're prescribing, that total force density. All right. And so this is very nice because, now given this force density F, we can actually solve this PDE for the fluid velocity, and then talk about, okay, how close is slender body theory to this PDE that we've come up with. Sort of the remaining obstacle in doing that, though, is that we do have this constant that's appearing in the energy estimate. And so we do have to go and be careful about precisely determining how that constant depends on the filament radius as the filament radius goes to 0. All right. And so there's a few inequalities that we have to check just to verify or to be sure, or to build in any epsilon dependence that might arise. So in particular, there's a Korn inequality, a sort of quasi 1D trace inequality that we have to be careful about, and then a pressure estimate as well. And it turns out that out of these three, it's really only the trace inequality that we really have to be sort of worried about, in particular because it does blow up as epsilon goes to 0. So in particular, we get a root log epsilon dependence as epsilon goes to 0. And so that's something that we'll have to build in and be careful about. In particular, if slender body theory is going to be a good approximation to this PDE, it should, also be, it should also capture this root log epsilon dependence, right? So it should be better than, or it should be closer than root log epsilon if it's going to be a good approximation. All right, so just to summarize just the well-posedness theory for this PDE, right? We have, a unique solution to this slender body PDE that satisfies an energy estimate with root log epsilon dependence. Right. Okay, so now we have this PDE. Now we can move on to really the main question, which is, how does slender body theory actually compare to this notion of true solution that we've developed? Right. So in particular, in order to answer this question, we have to use the slender body expression, which I've written out in a bit more detail here, just to kind of show all the terms that are that show up in there, to compute two error sources now. So there's one error source arising from, okay, if you take this expression and actually evaluate it on the surface of the filament, there's going to be some angular dependence, right? It doesn't actually completely cancel out that angular dependence in the velocity field, right? Okay, but it almost does. So it cancels that angular dependence up to an error of order epsilon log epsilon. And then there's also an error in using this expression to compute the total force per cross section. But that error is just bounded by epsilon. And so putting these two error sources together, along with the energy estimate that we had before, we can get an error estimate between slender body theory and this notion of slender body PDE. And so in particular, the difference between slender body theory and the slender body PDE solution does go to 0 as epsilon goes to 0. So in the fluid domain, it goes to 0 like epsilon log epsilon as epsilon goes to 0. All right. And then if you then go to the velocity of the filament itself, then you can also obtain an error estimate. And we see that extra root log epsilon dependence appearing in there from the trace inequality. Right. But again, we still get that the difference between this PDE solution and the slender body approximation goes to 0 as epsilon goes to 0. Okay. So from there are a lot of sort of natural questions to be answered about other scenarios. So in particular, a similar error estimate can be shown in the case of free ends, where now you have to have fiber radius that varies along the length of the filament. In particular, has to go to 0 at the endpoints. And you can obtain a similar error estimate as long as your force decays smoothly to 0 at the endpoints at the same rate as your radius. Then you can think about using slender body theory to approximate rigid fibers with crazy shapes. You can think about variations of slender body theory. And we also created a numerical method based on layer potential formulation of slender body theory. And so in that way, we were able to kind of numerically verify this convergence result. But one sort of application that I want to talk a little bit more about is what I call the slender body inverse problem. So thus far, we've been considering the case where you prescribe a force density along the filament and use that to then solve for the velocity of the filament, right? So it's really this map that's taking a force density to the filament velocity. So it's kind of a notion of a slender body Neumann to Dirichlet map, right? And in this case, right, as we've seen, the slender body approximation is a good approximation of this PDE solution, right? So taking the force density to some slender body velocity. But it's sort of equally valid, equally of interest in the, from an applications perspective to ask about going the other direction. So what if you want to prescribe the filament velocity and solve for the force density along the filament, right? So instead you prescribe U, you want to solve for F. And so from a PDE perspective, this is actually much simpler. It's just the Dirichlet problem for the Stokes equations, right? So we just happen to be giving it a boundary velocity that's independent of the angle over the cross section, right? So there's kind of no difficulties there. Really, the main difficulty in answering this question is that slender body theories actually turns out to not be very well behaved for this question, right? And so go into a little bit more detail in a minute, but just to recall, so along the filament center line, we have this force to velocity map that's given by a local plus non-local operator that kind of have this really sort of nasty looking form, right? And so if you want to invert this thing, you actually run into some difficulties. So we'll go into a little bit more detail about that. And in order to go into a little bit more detail, I just want to consider a model scenario, first of all, where, we're going to take a very important model geometry of a straight but periodic filament, right? So we have a straight filament, but with periodic boundary conditions at the end, periodic ends. All right, and the reason why this geometry is so nice is that we can actually explicitly calculate the spectrum of both the PDE operator and slender body theory. All right, so starting with the PDE version, right? So we're looking for the eigenvalues of this problem here, right? So lambda satisfying, force density along the straight periodic filament equals lambda times filament velocity. And this can be solved explicitly. It decouples into the tangential direction along the filament and then the directions normal to the filament. And these eigenvalues come in the form of a pretty nasty looking ratio of modified Bessel functions. But since Bessel functions satisfy a lot of very nice properties, we can show that these eigenvalues in both directions grow linearly as k goes to infinity. So in particular, doing this velocity to force map along the filament is very much like the usual Dirichlet to Neumann map, right? It's just like taking one derivative. All right. Okay, but what about slender body theory? What about using this nasty local plus non-local operator to try to do this velocity to force map? All right, well, here we run into some issues because, again, we can explicitly calculate the eigenvalues in the tangential and normal directions. And plotted here, so in blue, is the PDE spectrum lies along this line here. And we can see that for the slender body approximation, which is in red, in both the tangential and normal directions, they agree very well at very low wave numbers. But then at high wave numbers, right, there's a 0 in the denominator. They blow up, right? They disagree wildly at wave numbers that are proportional to, beyond wave numbers proportional to 1 over epsilon. All right, and so, but hopefully we can use that they agree very well at low wave numbers to sort of salvage the situation. And one way, or a couple ways that we can do that, is to consider various regularizations of this slender body operator along the straight periodic filament, right? And so one thing we can do along the straight periodic filament is to just consider a truncated Fourier series for the slender body approximation, right? And so, right, we can just take slender body operator and just cut off at some finite wave number, right? And so, this is something we can only really explicitly do for this model geometry, but what this regularization does is mimic the effect of numerical discretization, right? So, you just ignore beyond some fine enough discretization, all right? Okay, so that's one regularization we can consider. Another regularization is what I call the delta regularization, which is just to, in that non-local operator, insert a small parameter proportional to epsilon, and then use that to sort of alleviate the problems that we were running into. And in that case, again, we can explicitly calculate the eigenvalues of this operator. And instead of blowing up at finite wave numbers, so this is for two different choices of regularization parameter, instead it just approaches some asymptotic bound. And then instead of diverging, exponentially from slender body theory, or from the slender body PDE, it only diverges linearly at high wave numbers. Okay. So it turns out that both of these regularizations have the effect that we want them to have, which is that given a velocity of the filament, we can show that if we take this slender body Dirichlet to Neumann operator, then we can bound that difference in the resulting force density by something that goes to zero as epsilon goes to zero. So in particular, this difference goes to zero like epsilon squared. And that's for both the truncated operator and this delta regularized operator. All right. Okay. So this is good news, and it kind of segues into the second part of the talk, which is to consider now dynamics. All right. So in particular, I want to sort of be able to understand, for example, kind of the things that we were seeing on the very first slide in the video of the waving filaments, right? Okay, so what we've done so far is we've succeeded in making sense of this slender body Neumann to Dirichlet map in 3 dimensions, right? So we have this operator that's taking a force density along a curve, and it's spitting out this velocity field that we're taking to be the velocity of the filament, right? And so now we want to actually consider dynamics for this filament, right? So we want to consider a no-slip boundary condition, right? So that velocity at the filament surface is going to be the velocity of the filament, right? So, okay, we have filament velocity, and then for our force density, to kind of close our system here, I want to prescribe a very simple elastic theory, just Euler-Bernoulli beam theory. All right, so really the evolution will be due to the fourth derivative of the filament center line, right? And then this will be coupled with an inextensibility constraint. So there's a Lagrange multiplier to enforce that, okay, the filament doesn't grow or shrink in length over time. All right. Okay, so I can consider this filament evolution, right? This is what I want to be considering. All right, and so we can see now that understanding this operator L is important, right? This L epsilon operator is important because, the using the full classical non-local slender body theory to try to understand this evolution, it won't work because of those kind of high wave number problems, right? But one simpler problem that we can consider first is just using local slender body theory, which is where you just essentially just ignore the integral term in the slender body approximation. And so we can use local slender body theory to kind of understand what should this evolution look like, right? And so you can, and since this is just really just matrix multiplication, you can essentially say everything you want to say about this evolution in the case of local slender body theory. So in particular, you can get local well-posedness and small data global well-posedness, even in the case of when there's inextensibility. And what does this evolution look like? Well, you can, when you give it some sort of internal forcing, you can then determine, okay, what kinds of evolution, or what kinds of forcings are going to lead to swimming versus what kinds of evolutions are going to just lead to, well, a filament that just kind of flops around and doesn't actually move anywhere. All right, but that's all using just local slender body theory, right? So what we really want is to do kind of the full PDE, understand really what the slender body PDE will give us for this evolution. And so in order to do that, we really need more detailed information on the mapping properties of this Neumann-Dirichlet operator L epsilon for curved filaments.
Well, just quickly, the previous equation is torsion.
No, it's the tension. It's really the tension.
Okay. But it's an inextensible body.
Yeah. So this is So in this scenario, it's inextensible. So it can't grow or shrink in length over time. So it's always length 1 in this case.
What do you do at the end?
So the ends are force and torque free. So it's really just So in this case, it's the third and second derivatives that vanish of XSS first and third.
Okay.
Yeah, I mean, so I actually, when I do this, I consider it at the level of the curvature, and so it's the 0th and first derivatives of the curvature that vanish.
No, that's not so good.
So in the simulation, that's a periodic domain, or you're imposing those boundary conditions?
It's those boundary conditions. It's not a periodic domain. Yeah. So this is for local slender body theory, it's free ends. It's not periodic. So I mean, it's simple enough that that's feasible. When you go to the full slender body PD, that's definitely periodic boundary conditions at the endpoints, because then it becomes much more challenging to talk about the endpoint conditions. But okay, but so for the full PDE operator, sort of the strategy here. Well, so we really need kind of the details of the mapping properties of this Neumann-Dirichlet operator. And the strategy is, well, we have all the information that we could want in this model geometry of straight periodic filament. And so let's use that information and try to show that this curve, in the case of curved filaments, the full PDE operator is close to the straight periodic operator, right? And so this is kind of the strategy used to study the Muscat problem or water waves, for example. And so, but I want to start off with a kind of a toy problem, just kind of to see if this strategy will work. And so I want to consider the slender body Laplace equation here. So it's just same type of boundary conditions, where we have taking the total Neumann derivative per cross section is our theta f, and then u is independent of cross sectional angle along the filament, right? So it's just the Laplace analog of this slender body PDE. So now in this toy problem, I can consider the more detailed properties of this map taking f to u. And so let me denote the straight but periodic case by L bar. And in this case, so again, as was true for the Stokes case, we can explicitly calculate the spectrum in the straight but periodic setting. And L epsilon inverse, I guess, is given by a Fourier multiplier that we can explicitly write down, just ratio of Bessel functions again, right? And so what we can show for the Laplace setting, all right, so we can we know kind of everything that we want to know about the straight periodic filament because we have explicit Fourier multiplier. But then what we can show for more complicated geometries is that this operator taking the force density to the filament velocity can be decomposed into the straight operator plus two remainders. One remainder, which is smaller in epsilon, and another remainder, which is smoother, right? Okay, and so this is kind of the strategy for approaching how we will approach the dynamic problem. And sort of the proof of that or to show that you can decompose the operator in this way, you can relate F and U using using a layer potential formulation of the slender body PDE, where S and D are now just the single and the double layer potentials. And then use that, again, in the straight periodic setting, we can explicitly calculate pretty much anything we want to calculate. So these single and double layer potentials in particular, we can explicitly calculate how they act as Fourier multipliers, and then use that to decompose our slender body Dirichlet to Neumann operator as a straight operator plus some remainder terms that we can bound using this explicit information plus some singular integral estimates. Okay, so just as a, then where's this heading? So of course that's just the start, right? I mean, so the idea is to then hopefully be able to do this same kind of decomposition in the Stokes setting, right? So now to take the Stokes slender body Neumann to Dirichlet map and decompose it as, well, the straight operator, which we know everything about, plus some remainder terms. And then using that, be able to hopefully show local well-posedness, starting with the case of an extensible fiber, so removing that inextensibility constraint. And ideally, be able to say something about the limiting dynamics as epsilon goes to 0. I'll say that the ideal problem is to have the inextensible filament, but the inextensibility constraint does introduce a lot of additional challenges. Even in the case of local slender body theory, it makes the analysis a lot more challenging, and global existence for large initial data is I actually don't know how to do that when inextensibility is enforced for local slender body theory. And so that's yet another thing to address. And then sort of a long-term ideal is to actually be able to obtain this slender body theory, or this slender body PDE, as some limit of actual 3D elasticity along an actual elastic filament, and hopefully in the end be able to establish kind of a full hierarchy of models starting from 3D elasticity all the way down to local slender body theory. All right, and so that's the end, and happy birthday, Alexis, and thank you.